now comes the question as what happens as k tends to infinity, right. So, if we go back to this, I hope it is clear why each one of the n curves will start from an open loop pole at k equals 0, right. Now, out of these m curves will terminate at an open loop 0 as k tends to infinity, and the remaining n minus m curves will go to infinity in the complex plane along what are called asymptotes, right. So, now what is going to happen, right. So, the same equation I can rewrite this as 1 divided by k times s plus 4 times s minus 1 then plus 1 equals 0, right. That sounds very strange, right. Now, if I put k to be infinity, I get 1 to be 0, right. That is not exactly what we want to convey, right. On the other hand, that is why I am saying, like I am not doing a very tight proof, I am doing a very logical argument here, right. Suppose on the other hand, you write this 1 as let us say 0s plus 1 and 0s plus 1. Can I do that? Right. So, in a certain sense, when k tends to infinity, I am going to have the closed loop pole s tending to infinity, okay, in the complex plane. It can be in any direction, right. So, that is why the second statement comes into play, right. So, if we had m to be non-zero, in this case m was 0, right. In our example m was 0, n was 2, right. Since m was 0, like I do not have any branch of the root locus terminating at an open loop 0. Suppose m were 1, suppose, let me write it as an example. Suppose if we had this equation to be like this, rather than this way, minus 1 would have been an open loop 0. So, immediately you can see that if you rearrange this equation, we would have got this, right. So, as k tends to infinity, s will tend to minus 1, right. That will be one of the closed loop roads. So, that is why like there was a statement, out of the n branches, m branches will tend to open loop zeros if there were any, right. Other n minus m branches will tend to infinity along what are called asymptotes, okay. We are going to come there, right. So, I hope the logic is clear, right. So, as to why we have that what to say behavior. In this particular example, we do not have any what to say open loop 0. So, we are going to have two branches, both the branches going to infinity in the complex plane, okay, as k tends to infinity, okay. So, that is what is going to happen, right. Okay. Is it clear, the first step? Yeah.
How you started off with the open loop concept of going towards one test point, and then you came to this, that is,
I only took an arbitrary test point to get the angle condition, right, is it not? Now, we are starting the construction of the root locus. Let us say we focus at minus 4, right. So, we agree that one branch would start from minus 4, right, from this equation. From the equation in the red box, substitute k equals 0. What will you get? One of the closed loop poles as k tends to 0. I won't say substitute k equals 0 because it does not have any meaning as such. As k tends to 0, you will agree that the closed loop pole tends to minus 4, right, one of the closed loop poles. So, let us say I look at minus 4, I can have a test point going in any direction, right, the branch starting off at any direction. We eliminated the what to say entire space other than the real axis by arguing that there is only one branch, right. If there were a repeating set of open loop poles at minus 4, we could not dismiss that possibility, right. So, but since there was a non-repeating open loop pole at minus 4, we have only two options, one to the left, one to the right, and then I apply this angle condition, that is it. So, now we have the what to say set of test points to be limited, right, in this step. So, to show you how it started, I use this one. Is it clear? Yeah.
So,
yeah.
There was a third point, right? Here, the remaining n minus m curves will tend to asymptotes as k tends to. So, what does that mean?
We are going to come there, right? We will come in point number 3. Okay. So, what it means is that See, as k tends to infinity, the first term goes away, right? So, as I told you, this is not a very tight way of showing things, but then like imagine, that is why I told you this example, right? So, in this case there was one open loop 0. So, what happened is that, so let me pull these things up, right? As k tends to infinity, s plus 1 becomes 0, s equals minus 1. So, you have one branch going to an open loop 0, but then there is one more branch, right? What would happen to this? So, what the way people will demonstrate it, you know, like without going through the proof and so on, is that like, let us say we multiply this by 0 s plus 1, the product remains the same. It is as if like you make the number of terms to be equal, and you see that s tending to infinity is another root. Okay, that is what happens here, right? So, because what I did was that I replaced this 1 with 0 s plus 1 and 0 s plus 1. Okay. So, 0 being, right, or if you do not prefer 0, you put epsilon tending to 0, because we are looking at the limit analysis, right. So, you write epsilon s plus 1 times epsilon s plus 1, epsilon being very, very small, right, the product will tend to 1, right. So, essentially you will see that the value of s tends to infinity, right. How it goes to infinity, we are going to find out, right. So, as I told you, you know, like I am not doing the derivation, I am only giving you a logical, an intuitive process. I am not writing things very carefully, right, please remember that, okay. So, we are only doing a limit analysis here, right. So, that is something which we should remember. Is it clear? Is the first step? Okay. Now, let us go to the second step. So, root locus is all about following these steps, okay, like logically, that is all there is to it, right. The second step is to locate the root loci that lie on the real axis, okay. This is determined by the open loop poles and open loop zeros that lie on the real axis alone, okay, we will see why. Choose a test point on the real axis. If the total number of real open loop poles and real open loop zeros that lie to the right of this test point is odd, then that point lies on the root locus, okay, that is the condition, okay. Now, let us look at the first statement here, right. This is determined by the open loop poles and open loop zeros that lie on the real axis, right. Why is that true, right. So, why I can have complex conjugate open loop poles and complex conjugate open loop zeros? I can have, right. But then it so turns out that if I have complex conjugate open loop poles and complex conjugate open loop zeros, their angle contribution to any test point on the real axis would be you can call it either 0 or an even multiple of pi, it will cancel off. Right? Think about it. Let us say, as an aside, I do this. Let us say I had two open loop poles like this, right? And let us say I take a test point like this. So, the first test point is this way, the second test point is this way, right? What is the angle contribution from this test point? It is this, right? What is the angle contribution from this test point? It is this. So, what do you think will be the sum of the angle contribution of these two vectors? Depending on how you look at it, either they will cancel off, or it will become either 0 degrees or 360 plus or minus 360 degrees, right. So, depending on how you count, right. But certainly you see that it is going to become it is not going to matter as far as locating points on the real axis is concerned, okay. That is why we are only going to consider real open loop poles and real open loop zeros, okay, for step 2, okay. So, step 2, okay, is to locate the paths of the real axis that lie on the root locus, okay. So, for this what we do is that in this example there are no complex conjugate open loop poles and open loop zeros, but as we looked at it, what we need to do is that we need to consider only the real axis, okay. So, I am going to draw the real axis and then like consider just the real axis of our problem, right. So, we consider a open loop pole at 1 and minus 4. So, what happens is that we are going to consider 3 test points. let's say ST1, ST2 and ST3, right. So, you see that the open loop poles and open loop zeros divide the real axis into three regions, right, minus infinity to minus 4, minus 4 to 1 and 1 to infinity. Do you agree? The real axis is divided into 3 chunks, right, in this example by the real open loop poles and real open loop zeros, right. So, minus infinity to minus 4, minus 4 to 1 and 1 to infinity, right. Now, the question is that like which of these points lie on the real axis, right. Once again you need to apply the angle condition. So, if I take test point ST1 which is in the region minus infinity to minus 4, do you think the angle condition is satisfied? No, right. Theta 1 is 180, theta 2 is 180 degrees. So, it becomes an even multiple of pi. So, this region does not lie on the real axis. What about minus 4 to plus 1? See what am I using in my arguments? This diagram which we drew, right, this condition. We are evaluating this question, right. Okay. So, for a test point which is between minus 4 and 1, is the angle condition satisfied?
Yes.
If you take ST2, you see that theta 1 will be 0, theta 2 will be 180. So, this is right. Now, what about 1 to infinity? No, because the angle will be 0, okay, which is not an odd multiple of 180 degrees. So, this consequently tells me that the only portion which lies on the root locus is the region between minus 4 to plus 1 on the real axis, okay. Okay. Of course, we are going to do more steps, but as far as the real axis is concerned, for this example minus 4 to 1 is the only portion, okay, that lies on the real axis. How do we generalize it, from this example? That is what this document is about, right. What was the condition? Choose a test point on the real axis. If the total number of real open loop poles and real open loop zeros that lie to the right of this test point is odd, then that point lies on the root locus. If it were 0 or an even number, then that point is removed. So, let us go to our file once again, example once again. Let us say you take ST1, look to the right of ST1 on the real axis. How many real open loop poles and real open loop zeros can we count? 2, right, minus 4 and plus 1 to the right of ST1. Please remember the condition, right. You take a test point on the real axis, look towards the right of the test point on the real axis, consider only the real axis, okay, not the complex plane entirely, right. Now, you count the number of real open loop poles and real open loop zeros to the right of this test point, right. How many do we get? 2. Is that odd? No, that is why we can eliminate, right. Okay. Of course, the first elimination, this calculation I did by using this theta 1 and theta 2, but imagine, like I can have a general system, right. How do we simplify, how do we generalize, right, that is what we are doing. So, but then if you take a test point ST2, you look towards the right of the test point. How many real open loop poles and real open loop zeros do we have? Only 1, right, there is one open loop pole at plus 1. So, is that an odd number? It is, right. So, that is why we have ticked the region from minus 4 to 1. Is it clear? Okay. Now, 1 to infinity, you take ST3, you look towards the right of ST3, there are no open loop poles and no open loop zeros to the right of ST3, right. So, we can immediately discount that region, okay, 1 to infinity, okay. So, that is how we get this condition, right. Yeah. So, in that basically that is the generalization of what we discussed, right, as far as locating the root loci on the real axis is concerned. Is it clear what we did? That is step 2. Yes.
The odd number should be m or n plus m?
Does not matter, it should be some odd number. Okay. So, we are not worried about n and m here, because I am only looking at open loop poles and open loop zeros on the real axis. in this particular case, you know, like n happens to be 2 and both open loop poles lie on the real axis, but that need not be the case always, right? This condition, you just need to look at the fact that, you know, like when you take a test point on the real axis, look towards the right and the count should be odd, okay? Because I can have an arbitrary distribution of real and complex open loop poles and open loop zeros, right? Okay. So let's not relate them to n minus m or n minus m minus 1 here, right? So that will not hold true in general, okay? So we just want anyway odd and even. And I will tell you the logic, okay? Like if for people who are interested in generalizing it, the logic has to do with the angle condition, right? So because in this particular example we did not have a 0, but think about it. If we had a 0, that would contribute a positive angle, right? Is it not? Right? And this will be a negative angle. So that's why we are only looking at the whether it's an odd, we want the difference to be odd, right? So that's why, because any test point on the real axis will contribute either plus 180 or minus 180 with the open loop poles and open loop zeros that are on the real axis, right? That's why we want an odd number, because we want an odd multiple of 180 degrees here, okay? But please note at this juncture, please note that the steps will be different if k were negative. Why? Because here we took k, the phase contribution of k to be 0, right? If k were negative, what will be the phase contribution? It will be 180 degrees, right? So things will change a little bit, okay? Anyway, we'll come there, you know, like later on, okay? Yeah. Yes, please.
If there was a 0 in between or somewhere, we would use the same condition.
Same condition, no change, okay? That's why these are general steps, okay? Suppose if there were 0, right? Let us say we had this example, right? So let us say to answer that question, let's say we consider the real and the imaginary axis. This is plus 1, minus 4 and minus 1 was the 0, right? So same steps, but now the only thing is that you will have 4 regions, minus infinity to minus 4, right? Minus 4 to minus 1, minus 1 to plus 1 and 1 to infinity. So if you use this, you will see that minus infinity to plus minus 4 will now be on the real axis, because any test point here will have 3 open loop poles and open loop zeros to the right. This will no longer be there. Minus 1 to plus 1 will be giving you an odd number. This will not. Okay, so that's the difference which you get, right? So once you have the 0, okay, so that step is generic enough, right? Okay, so we'll do steps 3 and further tomorrow, okay, in the next class, because I think explaining these steps also, what to say, and discussing them are pretty important, okay? So, but then what I request you to do is that, like, kindly look at this document from the course website. Please read through the steps and come prepared for tomorrow's class, okay? So at least you have read them once, okay, and think about the questions that I asked of you, all right? Okay, we'll continue tomorrow.